Hello, I'm Mario Graf, and today I'm going to talk to you about Hertz law or Heaps law. This is natural language processing, and I'm Mario Graf. Well, Heaps law allows you to predict the number of unique tokens or the size of the vocabulary. That's another way of saying that you are going to obtain when you read a number of tokens. The cardinality of P, we are going to tell that we are going to define as the number of types or the number of unique tokens or the size of the vocabulary, and that is the dependent variable, so the variable that we want to model. And the Hertz law that has this form allows you to given the independent variable, which is the number of tokens, so the size of your corpus, just put it in that way, we can predict how many different words are we going to have, or the size of your vocabulary. So in order to do that, we need to identify some parameters, which are beta and k. Let me try to make an example. For example, if we have like 3 million tokens, so we have read 3 million words, then what we have is more or less like 80,000 different tokens, or the vocabulary that we have read is 80,000 words, different words if the tokens are words. So how the problem is that given a set of points, given kind of these points, what we want to know is to find for a particular language or for a particular combination which are the values of k and beta. So I'm going to explain here how are we going to identify beta and k, and then we are going to have like two examples showing what happens if we change the parameters of the tokenizer, how it's going to affect the parameters beta and k. But first, let me try to make this as slow as possible. What we imagine that we have a set of points. These are the set of points that we have, and what we want to we have this set of points. You may say, okay, this is quite different than the points that we have seen from Heaps law, and yes, it is. They are very different, but you may think, okay, this looks like a parabola. Yes, it looks like a parabola. So if we have a set of points, this set of points, and you say, okay, this is like a parabola, so the problem in a parabola is to identify the coefficients a, b, and c. These are the coefficients that we want to identify. So these ones are the coefficients a, b, and c, and the equation that models a parabola is this one. I'm using hat y in order to make clear that we are modeling something. So this is the variable that we are going to, this is the notation that we are going to use to identify a model, and without the hat, without this one, what we are going to say is the points that we are measuring. Imagine that these are points that we measure from some device. So how can we identify the coefficients a, b, and c? Well, the coefficients of a, b, and c can be identified using ordinary least squares. I'm going to go through the details of ordinary least squares. So you have a set of points, all the blue points. Let's look at and you kind of say, okay, these points looks like a parabola. The equation of a parabola is this one. So each individual point, once we have identified a, b, and c, we can say, okay, each individual point, the point I, it's going to be modeled using this equation, and it is going to be approximately equal to the point yi that we measure. So let's try, for example, this point, which is approximately, because I'm just going to point with the mouse, so I'm not going to give an exact value of this point. So for example, if we look at this point, okay, this is almost 0 in the independent variable, and the output or the dependent variable it's approximately 3. So we say okay, this, and we can say the same thing for all the points that we are seeing. So the first point that we see is this one, which is -1, and the output or the associated value to this to the input -1 is 18. So what we want in ordinary least squares is to find the coefficients a, b, and c such that for all the points the model follows as closely as possible the points measured. So in mathematics we can say that using an error function, which is this function. This is the error. So this is the we want this value, which is the value that we are measuring, the y1, and this is the predicted value. We want these two components or these two elements to be as similar as possible, so that the error between them it's the error is the square error. This is the error, and the whole term is the square error. If we sum all the errors, I mean, from all the observation, this is what it's saying here. So it is the sum of all the square errors is equal to 0. So we want to be 0. We are not going to go that far. I mean, there are going to be some errors that this value, this sum is not going to be 0, but we want it to be. So in order to model this, we can follow two approaches. One approach is using calculus, so you use the derivative of this equation, and the other approach is using algebra. We are going to follow the second one. So we can define a vector a1, which is the square of all the independent points that we have measured. Remember, these are the independent points. So for example, here is the 0, and the independent points goes from -1 to 1. So the vector a1 contains the square of all the independent points. The vector a2 contains all the points, all the values of the independent points. The vector 1, it's only a vector of ones. These are column vectors. So you can see here is the transpose. With these elements, we can create a matrix A. The matrix A is just the first column of the matrix A. A is the vector A1, then A2, and then the column 1. Using this notation, we can also define a vector X, which contains the coefficients that we want to identify, which are A, B, and C, also a column vector. And the output, or the predicted value, or the dependent variable, are y, and it is also a vector that contains 1, 1 until 1n, which n stands for the number of points that are in this graph. Using this notation, this can be expressed mathematically. What we are trying to find is we are trying to find the coefficients x, that when the dot product between a and x equals the vector y. So we can solve this linear equation. Remember, it's a linear equation. We can solve it using a little bit of algebra, which requires setting up the transpose of A, and then the inverse of that operation, and it outputs something like that. So if we compute this, then we are going to obtain the coefficients x. The coefficient x, which contain A, B, and C. Okay. This is a determined deterministic algorithm, or ordinary least square, is deterministic, and it is not iterative. I mean, there are a constant number of operations in order to solve this system of equations. Now that we have found the coefficients a, b, and c, we can plot it. We can use these coefficients to plot the parabola, which is represented by the orange line. And as you can see, well, it follows closely the points, but not exactly all the points are in the line itself. Now ordinary least square can use to solve the problem of finding k and beta. Well, unfortunately, no, we cannot use ordinary least square to solve this problem, because ordinary least squares is a linear estimator, and the coefficients that we are trying to identify are not linear cannot be linearly identified, because as you can see here, n is the independent variable, and beta is a coefficient that we want to identify, and it is the exponent of the independent variable. So what we can do in this case, we can use iterative optimization methods in order to find k and beta. Let me try to define an optimization problem. Well, imagine you have a function f where the input of that function is a vector x that lives in a d-dimensional space, and the function returns a number. So a minimization problem is defined as the following. You want to find from all the points that are in the vector space D, you want to find the point x that makes this function as minimum as possible. That is a minimization problem. You may wonder, what about if I have a maximization function that I want to optimize? Well, if you have a maximization function g, then it is equivalent to minimize the minus g function. So if you have a maximization problem, you can convert it trivially to a minimization problem. So it really doesn't matter if you are talking about minimization or maximization, but for now we are going to talk only for minimization. Now, if we need to, in order to identify k and beta, what we need to do is to pose this problem as an optimization problem, particularly a minimization one, and then use an optimization algorithm. So the first step is to define the function f that is going to be minimized. That function, as we have seen from the problem of finding the coefficients a, b, and c of the parabola, we need a set of points. So the first step, let x be the set of points that we are measuring. So the set of points, this is the number of tokens that we have read, and the cardinality of b are the number of the size of the vocabulary for these tokens. And for these other tokens that we have read, this is the vocabulary that can be built reading these tokens. Now, a little bit of constraints, just a little bit. This is not necessary, but this set x is kind of order, so n1 is less than n2, and so on. And the error function, if you remember, the error function that we have seen on the parabola is just the sum of the errors to the square, the sum of the errors to the square. So we can do exactly the same here. So the error function is if we if we sum all the points that are in x it's have two values, the value of n that corresponds to the number of tokens that we have read, and b to the vocabulary. So what we want is that the vocabulary that we have measured is similar. So the error between the vocabulary and the vocabulary that it's going to predict with the Heaps law is quite similar. It's a small error, such that once we have defined beta and k, this term is going to compute the error, and in order, it might be a positive or a negative, but in order to keep all the numbers positive, we square the error and we sum over all the points that we have seen, and this is the function that we want to minimize. The function that we want to minimize has two parameters, which are the parameters k and the parameters beta. The parameter k and beta. Now, I haven't described how to create the set of points given a document. So imagine we have a document. This is the algorithm that we are going to use to create, to compute the number of tokens and the vocabulary. So we start with a document. We also require a tokenizer. We have discussed what is a tokenizer. And we require a dictionary. A dictionary is a data structure that it is a key value data structure. So on the keys you are going to have the words, and on the values you are going to have a number that indicates how many times that key or that word has been seen during the reading of the document. So you tokenize the document and you iterate for all the tokens in the document D, and you count the different types or the different words that you see. So for the word W, you are going to say, okay, how many times I have seen the word W, and given that this is an iteration, we have seen at this point we have seen one time the word, plus one time the word that we are seeing here. So if we haven't seen the word, this is like a comment. Well, this is a comment. If we haven't seen the word in the vocabulary, what we are going to say, okay, we are going to say that the mapping between key and value, the mapping, the B is a dictionary, so the mapping that goes when the word is W, it's going to be 0. So if we haven't seen the word, this is going to be 0 plus 1, and so the next time we see this token W, it's going to have the value of 1. You get the idea. Now, after we finish this loop, what we need to count is the number of tokens. We can also count the number of tokens here, but we can also do it outside the loop. And in order to do that, we only need to go to iterate for all the points, all the key value points that are in the dictionary B, and we are only interested in the second part, which corresponds the number of times we have seen a word, which is C. And we return, this function return the number of tokens that we have read and the size of the vocabulary or the cardinality of B. The function is called tokens type, and well, now that we have defined the function tokens type, we are going to use it. Imagine that we have a collection of books. The books are by B1, B2, until Bn. So we have a collection of books. This collection of books are going to be used to create the points that we are going to store in X in the list. We can say it is a list or it is a set X that it's formed by pairs, when the first part of the pair is the number of tokens and the second part of the set of the pair is the size of the vocabulary. So you have a list of books, you have a tokenizer, you define a tokenizer, you make a dictionary. At this time the dictionary is empty, and you define where you're going to store the points. You are going to store this, the output of this function in a list X. So you iterate for all the books, and the first book is identified by the variable b. You call the function tokens type that we have just defined. You pass the document, which is the one of the books. You pass the dictionary b. It returns a pair, if we remember, it returns a pair, and that pair is concatenated to what we have computed in the previous step. At the first step, the list is empty, but it is kind of a notation to say that we are going to append elements to a list X. And finally, we return X. If we do this, in order to kind of explain a little bit better this, or to have an idea more clearly, an implementation of this pseudocode, I'm going to implement it in Python. So we are going to use the I downloaded the 20 most downloaded books from this website, which is the Project Gutenberg. These books are in English, so I have 20 books. Let me try to explain how the tokens type function was implemented. So it received a file name, it received a counter or a dictionary. I'm saying here that it's a counter. It's kind of a class that comes in the collection, but it is a dictionary. It received a tokenizer. It say that it received a tokenizer. So the first step that you are going to do is to read the file name. You open the file name and you read its content. Then you tokenize the document using the tokenizer TM. So you have the tokens, and given that counter is from the class counter, there is a method that says update, and so the loop that was in the pseudocode is only a line here using the counter, which that line it is the update. So you update the counter, and then you need to compute the number of tokens that we have read in this step. So the number of tokens, as you can see, well, it is an iteration for the values of the counter. Remember that there is a dictionary of keys, and each key is a word, and the number indicates how many times we have seen that word in all the tokens that we have read. And we return this value, which is n in the number of tokens, and length, and the length of the counter is the number is the size of the vocabulary. So we have like 20 books. So the first step, in order to use this function, I'm talking about this function, we create an instance of counter, and then we iterate for all the file names that are for all the books that we have, or that I have downloaded, where I pass this iteration or this loop. As you can see, it is a list comprehension. So you go for file name, you pass the counter, and you pass a tokenizer, and you obtain in X, you obtain a list of pairs where the first part of the pair follows this notation. The first part is the number of tokens, and this is the size of the vocabulary. If we plot this list that we have just created, it looks like this one. So it is the same example that I have been presenting since the beginning. If you have like 3 million tokens, then you will have 80,000 words, a vocabulary of 80,000 words. Okay, so far we have seen these two steps. We have defined the function f to be minimized, but it is missing the error function that we are going to use. So the error function, which is kind of very nicely expressed in mathematics, can be expressed in Python using this notation. The minimization function that we are going to use receives a vector. So the error function receives only a variable which contains a vector, which I'm going to call here coef. And now it is time to look for in our points x, we are going to look for the values of the dependent variable, or the output that we want to model, which is y. And we kind of have this as a list, or as a vector, can be seen as a vector, but in fact in Python it is a list right now of the dependent variables. Now for the other part, we need the independent variables, which are also in x. We only need to retrieve from x, and we create an array from numeric Python, and the variable where we store this is x. So we need the final step, or almost the final step, is we need to compute this Heaps law, which is the first coefficient, it's going to stand for the k coefficient, and the second coefficient is going to be the beta. And so this is the way we implement Heaps law. Remember that coef, it's a vector that contains the two coefficients that we need to identify. And finally, we compute the error, the square error, the sum of the square error, which is in this line. Once we have implemented all these steps, what we have done is to pose the problem of identifying k and beta as an optimization problem. So this step is already done, and the final step is to use an optimization algorithm. There are plenty of optimization algorithms. I'm going to click here in SciPy. There is a function that is called minimize, and contains different optimization, different algorithms that can be used to minimize a function. So we are going to use the simplest one, which is an heuristic. Remember that we have developed an error function. We have defined it in Python, and also, as I told you like 5 slides before, that it is an iterative optimization problem. So we need to say which is the starting point, since we already know that beta goes from from 0.5 or something to almost 0.9. So a good starting point is 0.7. So, and from the k I have no idea, so 1 it's fine. I know that it is not negative, and really k, although it is in Heaps law, it's not that important. It is more important beta. So, but anyway, I'm setting 1. This is the method that we are going to use, and these options are not necessary. This option is only indicating that there is the minimization function is going to be verbose. So we are going to see how many iterations it took to obtain the coefficients, to identify the coefficients k and beta. We run this program, and now that we have obtained k and beta, we can use it to we can use it to predict for any value of n. So this is the prediction, and we can see in the orange line that it is the Heaps law, and we can see that it follows closely the points that we have measured. But of course there are errors. For example, look at this. This is an error because the Heaps law is telling me that this point should be here, and we have measured and it is here. So it is not an exact model. It could be possible to find a better model, but I don't know if that is necessary, because it gives you an idea of something. It is not important to have a close prediction. So far we have seen how to optimize the functions, how to identify the coefficients k and beta in order to use the Heaps law. And the coefficients that we are seeing in this plot are this one. The beta is 0.79, But what about if we change the parameters of the tokenizer? For example, what about the use qgrams, or if we use lowercase? Right now, these parameters, these ones, were computed using all the words considering without changing the words to lowercase. So if you could have one word that that has an uppercase and the same word that it's in all lowercases, and these are different words, so these are two words in the vocabulary. So let me try to do an example here. I'm switching to the code, and I'm going to execute a little bit of this code. Okay, the first step, I'm going to execute what we have just seen. As you can see, there is the tokenizer and the function that we have defined, and then this is the counter. We have seen this in the slides. We have seen also this is in the slides, and so we can predict, we can plot we can plot what the points that we have computed is using different books, using these books. Now, what I was talking about is what happens if we change the tokenizer. So, okay, well, let me just try to complete this example. So this is the error function that we have seen, and this is finally the minimize function. So the optimization, as you can see, that it took 88 iterations to find the optimum, and we can ask for the final coefficients values, which are these ones. And if you look at the presentation, you are going to see that this is the value of beta. But what about if I change and, for example, say, okay, I want qgrams of 4. So what would happen? Let me try to run this. It's going to take a while. So while we are waiting, let me try to explain. Okay, a qgram of 4, it tells us that the maximum length of the word is going to be 4 characters. Normally, the words in English, well, I have no idea, but it seems like it is quite possible that the average length of a word is not 4 characters. It might be a little bit longer. So what you are imposing, if you say, okay, I want a vocabulary of qgrams of 4 words, is that you are kind of making a constraint on the number of possible words that you are going to have, which will be reflected in having a lower value for beta, which is here. As you can see, the previous beta that we have is 0.79, and if we constrain this, it's 0.67. But let me try to, what about if we use lowercase? Lowercase in our initial example is set to false. So, but what about if we change all the words to lowercase? Then, as it is similar, we are kind of making a constraint on the number of different words that we have, so that will be reflected on the value of beta. I hope it doesn't last too long to have the output of this computation. As you can see, it's 0.74, which is a little bit less than 0.79, which also makes sense. And, well, this is, I already write these numbers in case for trying to explain. As you can see, the parameter k range from 10 to 1 really doesn't make, it is not too informative, the parameter k, but the parameter beta is quite important because it tells you how the vocabulary is going to increase. So you can ask with Heaps law, you can say, okay, what is going to be the vocabulary if I read 10 million words? Well, it really depends on the beta, but we can have an example. We can use an example. So I have read 10 million words, and I have a beta of just say of this 0.74. So if if I have this beta, then the number of words is going to be 151,000 different words. But if I read a little bit more, for example, if I'm downloading the open stream of Twitter on English, we are going to download more than 1 million tweets per day. So if if each tweet has a little bit more than 10 words, we can have easily 10 million words, a corpus of 10 million words. Now, what about if I have 10 days of those? Then how many different words I have seen? Well, I have seen 803, approximately 800,000 different words. So you get the idea, and the Heaps load allows you to see how it's going to how it's going to increase the number of the size of your vocabulary as while you are reading and reading more and more books or more documents. We are reaching at the end of this presentation. If you have any question or comment, please do not hesitate in contact me. Thanks a lot.